Hello everyone, thank you for attending the seminar. My name is Hans Fraaije. I am founder of Culgi multi-scale computational chemistry company based in Leiden, the Netherlands. Since December 2020, 1 year ago, Culgi is part of the Simcenter portfolio of software products within the industrial software division of Siemens. Simcenter includes other packages as well, in particular computational fluid dynamics, Stokesian Plus, that we will return to at the end of the seminar. Today, I will be talking about an exciting new development within Simcenter, namely the discovery of novel algorithms for micro-rheology. Let us start with a realistic business case to understand the pain point we are addressing. The slide discusses a typical setup for materials discovery in a chemical company or personal care company. We will restrict ourselves to soft materials only. In the center of activity is a robot carousel where one aims to test thousands of recipes in a year. This could easily be in the order of a few hundred in a single day for a single robot. The robot is surrounded by all kinds of other activities. At the start is a mental discovery step where one tries to digest what the competition is doing. This is not further discussed here. Also, there is a computer with software that steers the design of experiments. Then, if everything goes well, a small fraction of tested recipes is handed over to the engineers for scale-up and production. Again, a rough order of magnitude. The chemists test maybe a few 100,000 recipes in a year, but the engineers can handle maybe only a few hundred for scale-up in that same year. That is 1,000 times less. In other words, the reduction is enormous. This is the materials pipeline in action. Why is it so difficult and time-consuming to scale up? Well, one of the reasons is that in scale-up, one needs to consider processing parameters, including rheological parameters. Not only does one need enough material to do that, kilogram quantities at least, but also one will need to do some sort of rheometry to steer and guide the selection of so-called constitutive equations. A constitutive equation, or CE for short, is at the heart of a rheology model. Simply put, a CE is a material-specific viscosity and elasticity law. And here is the problem. The experimental determination of viscoelastic parameters is extremely time-consuming and in many cases actually very difficult to do. Let's say a full parameterization of a realistic CE, such as multimode PTT, more on that later on, can take months of hard work for a single recipe. On top of all of that, many new formulations in polymer products are reactive, either in consumer application or in production, which means the formulation changes drastically as a function of time. Getting the experimental viscoelastic parameters for such reactive systems is extremely complex, if not impossible. Let's go to our solution. We will use advanced physics-based molecular simulations derived from the world of chemistry to calibrate the CEs that the engineer needs, in such way that the method can be used in early-stage materials discovery. This is really a handshake between two communities that so far have perhaps been too isolated. On the left, one has the simulation with force fields and molecules. On the right, CEs and continuum mechanics. East is east and west is west, and never the twain shall meet. Well, if we want to speed up the value chain, we need to figure out how to make the two communities work together. And the simulations have to be very fast too. Remember that simulations are competing with robots. We want our simulations to be fast in screening mode, just as happens in drug discovery. So instead of doing only a few massively parallel simulations, which is of course possible, we will aim to simulate for simulations that can return a result for a given recipe overnight on only a few cores. so that we can also do a few hundred simulations in a day, and that on only a few nodes on a cluster. It is like this. The chemist would say, engineer, tell me what viscoelasticity you need for an efficient and effective process, and I will add that to my virtual screening toolbox. The engineer would say, chemist, can you add something so that the stuff flows better, without affecting other properties, of course? The slide demonstrates the challenge that we are facing. In short, it says what are the difficulties in modeling modern materials with CEs. The CEs that could be applied are empirical, with a non-obvious relation with the molecular world. In our experience, we find that by far the most widely used CE is the generalized Newtonian fluid equation that has no elasticity whatsoever. The physics-based equations that do have some elasticity, such as Oldroyd B, are too simple to cover the complexity of a realistic industrial material or take too much time to calibrate, such as multimode PTT or POM-POM. The slide also hints at an application in Kevlar processing that we will be talking about in more detail in upcoming slides. Let's first take a step back and discuss briefly what molecular simulation method we could think of that could generate the virtual rheometry data that we need to calibrate the CFD. Up front, we assume that the chemists have done their job in coarse-graining the chemical ingredients. This includes the grouping of atoms into coarse-grained units, beads, and finding bonded and non-bonded parameters, and for reactive systems, the microscopic reaction constants. We will need those to feed into kinetic Monte Carlo. We could well use Culgi's ABC method, that is semi-empirical quantum, and Culgi's AFP, that is automated fragmentation and parameterization, for all of that, but alternative coarse graining could also be used. Notice that in industrial practice, where one wants a method to do this on a wide chemical space and fast. Remember the 100,000 recipes in a year. And for that, one needs automation as much as possible. But today, we will not talk about coarse graining, but about micro-rheology. In selecting the simulation engine, there is one very important theorem one needs to consider, and that is the so-called scallop theorem. This says that in a micro world, inertial forces are negligible. The engineers will call this the creeping flow regime. Now, if we scan through the available simulation engines, we discover very rapidly that many very popular molecular simulation methods are not applicable. This includes molecular dynamics, but also dissipated particle dynamics. So what is our solution? We recoded dissipated particle dynamics from scratch with the acceleration turned off completely. This is a non-trivial new algorithm that amounts to solving a large set of equations each time step. We call the new algorithm Stokesian Particle Dynamics to highlight that it operates without inertia. This is similar to Stokes flow, that is Navier-Stokes, with the Navier part removed. In fact, the new algorithm starts to have the look and feel of creeping flow algorithms in CFD. But in our case, we do not have a CE, but a full recipe of interacting chemical ingredients, down to the coarse-grained molecular level, with the enormous advantage of knowing in detail the chemistry. It is interesting that even with this information, we do sometimes get questions from the engineers as to what CEs we are using. The answer is, with what we do, constitutive behavior comes out. We do not put it in. A very short discussion of the validation. The graph shows the relaxation towards mechanical equilibrium in a virtual micro-rheometer. A homogeneous fluid of coarse-grained beads is captured between two plates. The fluid is mechanically ideal, meaning that it behaves as a Newtonian fluid. The top plate is given a sudden kick to start moving at constant velocity. This is a miniature virtual version of a Couette rheometer. The new algorithm SPD reacts just in the way we hope and expect. The reaction is instantaneous. The old algorithm, DPD, needs time to build up the equilibrium velocity profile. in fact weeks of calculation time, not because of intrinsic elasticity in the system, there is none in this case, but simply because of inertia. It takes time for the momentum to diffuse from the top to the bottom. And as we just argued, that is incorrect for micro-rheology in view of the scallop theorem. The artifact gets worse the bigger the system. In fact, the inertial relaxation time scales with the size of the system squared. The calculation of SPD took just a few hours to a day on an ordinary PC. Doing this with DPD would cost weeks. If one deals with simple small organic molecules liquids, then one can get around that by having a small simulation box and perhaps using an imposed velocity gradient and non-periodic boundary conditions. But when we go to microstructure formulations with potentially large objects, such as emulsions, fillers, large stiff polymers, and inhomogeneous viscoelasticity, not only does the artifact get worse because of the increased size, but also then we can no longer use the small molecule tricks of imposed velocity gradients and non-periodic boundary conditions. After all of this talking, let us go to a realistic application, making Kevlar. The slide shows the multi-scale approach from the Lewis structure to the coarse-grained polymer to the fiber to the kneecap protective clothing to the thatching of a roof. In the middle is a virtual cuvette micro-rheometer on a coarse-grained scale. First do the coarse graining by semi-empirical Cosmores. ABC has been published, the paper is indicated. And then we do the fragmentation. This has been published too. And finally, we turn on SPD for the reactions. What the movie shows, let me turn on the movie. What the movie shows is the formation of polyaramide by polycondensation, simulated by SPD augmented with kinetic Monte Carlo. The solution is 20%. We apply a constant sinusoidal body force to trigger a viscoelastic response. This is not cuvette flow. On a side note, I was at AXO in the 90s when they started building capacity in polyaramide production. Imagine the rheology of a concentrated solution made up of ultra-strong polymers. The viscosity goes sky high, a big issue for a production facility at that time because of the excessive heat generated and breaking of petals. A question to the chemist was then, and it is now, could one possibly modify the solvent to improve the process and generate IP on that? Back to our topic. We use a simple trick to get to the viscoelasticity quickly. We apply a sinusoidal body force. Let me turn on the video again. We apply a sinusoidal body force and observe the buildup of stress and velocity profile. This is exactly what we need to get to the CEs, the constitutive equations. That is, the temporal and spatial relation between stress and velocity gradient. Here it comes out of the molecular interactions. We did not put it in, as in CFD. We could also have done the cuvette flow setup, but there is an advantage to the sinusoidal body force that we will come back to in a moment. As the conversion proceeds, one clearly sees a few distinct viscoelastic behaviors. In the beginning, the system behaves as a Newtonian fluid, but after a while, one sees extremely shear thinning and even plug flow here, right in the middle. That is, the system develops a yield stress. Now, let us go to a different application. Polyurethane coatings. We can do this slide very quickly. I do not think we need to elaborate on the relevance of polyurethanes for this audience. As in the case of polyaramide, we will do a coarse-grained SPD simulation augmented with kinetic Monte Carlo, indicated on the right in a stylistic fashion. We will not discuss today foaming, that's on the left. That would justify an entire session at the conference, not just a few minutes in today's seminar. Let's go to the results. The same trickery as with polyaramide, when reactive monomers meet, there is a certain probability of bonding. That's the kinetic Monte Carlo. And the whole system is mechanically forced by the constant sinusoidal body force. There is one difference, however. Now the system forms a network instead of linear polymers. We have bivalent isocyanide monomers reacting with tetravalent polyols. The conversion plot is perhaps not very spectacular, but if we look inside, so to say, we see the network formation. These molecular simulations can of course easily be used to extract useful network characteristics, such as size distribution of molecules or network topology. It is also almost trivial to extract the mesoscopic morphology. That is the hard and soft distribution from the same simulation, but we will not do that today. This is a zoom into the network. It's quite spectacular, but it's just a nice picture. Slide 15. Using this simulation, we can also extract the viscosity versus shear rate as a function of conversion. This is where the sinusoidal body force trick comes into place. It allows us to get a quick and dirty handle on the viscosity for each snapshot in time by taking the ratio of stress and velocity gradient without the need for a virtual rheometer setup. We could also have reused the correct rheometer, of course, but this is more convenient. One clearly sees the development of a very strong viscosity as a conversion proceeds. Of course, the next thing to do is using these simulations to calculate the crossover from purely viscous to purely elastic behaviors, because that is definitely happening. That work is in progress. Now going back to the CFD software that we talked about in the first slide. This slide shows the available constitutive equations within the Simcenter CFD package *CCM+. For example, the list contains the power law or shear thinning model for generalized Newtonian fluids and also the PTT model for viscoelastic behaviors. Other CFD packages will have a similar list of equations. In fact, also Siemens G-Prom's engineering software has more or less this same list, so it could use the micro-rheology in manufacturing in principle. Conclusions. In this seminar, we have concentrated on demonstrating Stokesian particle dynamics as an exciting new coarse-grained simulation methodology and provided proof of concept. We have stressed the usability in early-stage materials discovery. The simulations we presented only take a core day or so and can easily be used in screening by distributing recipes over a cluster. We did not discuss the actual crossover to scalar models in CFD. We leave that to follow-up discussions aimed at engineers. To conclude, Stokesian particle dynamics is a new coarse-grained simulation technique suitable for micro-rheology. The connection with kinetic Monte Carlo opens the door to reactive polymer processing. Connection with CFD is through calibration of CEs, constitutive equations. The method is very fast and can be incorporated as a screening tool in early-stage materials discovery. Through Culgi Automated Fragmentation and Parameterization AFP and Culgi Semi-empirical Quantum ABC, the method is applicable to a wide chemical space. Thank you for your attention. This concludes my presentation.